let's get going. So let's continue with this. So we need to think about instantaneous velocity or instantaneous acceleration. I guess instantaneous displacement is like nothing because you are where you are. And this brings in a little bit of graphing stuff, or brings in calculus stuff. If this is my journey, so this is my, I call it coordinate, position versus time, and there's my journey. At any instant I can pick a point on my graph, and I can say, okay, well, what is my velocity? Well, velocity is change in position or displacement versus time, and that corresponds to drawing a tangent on here and saying, for that tangent line, what is my rise over my run? So you picked a point there, there's your delta t that you're interested in, there's your t that you're interested in, and you said, let's draw a tangent to this graph, and then we have a displacement for a given time. And if I do a bigger triangle, yeah, I get a bigger displacement, but I get a bigger time, and the ratio stays the same because it's a similar triangle. So, and if I want to do instantaneous acceleration, I have a velocity versus time graph. I pick a certain time, I draw myself a tangent, and I do, again, my rise over my run. In this case, my rise is not my displacement, it's my change in velocity. But in both cases, my run is my change in time. Duration, if you like. I can talk about that mathematically, and so what I get is that my instantaneous velocity, notice there's no bar on top of this. It's just rather than v bar, I just have v because it's instantaneous. So my instantaneous velocity is the limit as my little bit of time interval, if you like, as my run goes to 0 of the displacement over the duration. And that I can write as dx by dt. And my in terms of my acceleration, it's the limit as my time interval goes to 0 of dv by dt, of delta v by delta t, which is my dv by dt. And if I did some calculus, hopefully you did that. Well, dv by dt is d2 d by dt of dx by dt, which is d2x by dt squared. Yeah, you can get it from the second differential. Yeah. So what kind of question am I likely to ask on something like this? And it's like this, basically. I'm going to basically say, what is the instantaneous velocity of a particle whose position is defined by that? So that's a position versus time equation, where x is in meters and t is in seconds. And what is its instantaneous velocity at t equals 3 seconds? This is not essential, but I like to do it. And I somehow represent this. If I had time, I might actually go and put numbers in here to get an idea for what this thing looks like. But I'm just going to cheat for the moment. And I'm going to go like, oh, it looks like that. And then I'm going to pick 3 seconds, ... I'm interested in that point there. That's the bit that I'm interested in. But I'm not going to do it graphically, of course. I'm going to do it in terms of integration, differentiation. So I'm going to say x is equal to 2t squared plus 4t minus 7. So dx by dt, and I guess, is this what the power rule is this? 4t plus 4, yeah? And then you go at t equals 3 seconds, dx by dt, v, which equals dx by dt, equals 4 times 3 plus 4, which equals 12 plus 4, which equals plus 16 meters per second. Did I do that right? Yeah. So, and I'm not going to give you some, I'm not trying to catch you out on the calculus. I'm not going to give you some error function or some wacky thing that you did right at the end and you kind of like, can't remember it. It's going to be something like that. It's going to be, x cubed, x squared. It's, something that should be doable. I don't want it to be it's the calculus that trips you up. I want it to be that you don't know to use the calculus to trip you up. But if you can't do that calculus, then it will trip you up. You still got to get the answer right. And, yeah, why? Well, that's what we're doing. you guys, I think you know how to do this, so I'm gonna leave it. I did one example. I'm a bit behind. I don't want to get caught out. So watch out for that. Ooh, 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 ooh. Well, we get to it a bit later, but I'm going to talk about it now. So I'm going to just ignore this for a minute. I'm crossing it out just so that, you know, so that you guys know I'm talking about something else. I could also draw you a graph. I don't think I would do this very often, but I have done it. So I give you the graph on nice graph paper. So I'd have to draw it really well. And then I say, oh, this is 1 second, 2 seconds, 3 seconds. This is 1 meter, 2 meters. And I might say, so what is the velocity at that point there? And I'd want you to be able to get a ruler and draw that, and then be able to construct that triangle. And you could say, let's have a look, this is about 1, so that would be V is equal to 1 over, and that's going to be 2, so that would be 0.5 meters per second. I did that backwards, didn't I? That's 2 rise over run, which is 2.0 meters per second. Okay. It's much more likely you're going to get the differentiation form, but that's a possibility. Okay. Let me ask you a question. So on this number line, so imagine there's a number line. I'm on the number line. So where are my positive addresses in this room? Where are my positive addresses from your perspective? Over here, aren't they? All the positive addresses over here. Where are the negative addresses? So if I'm going in this direction, what's sign for my velocity? Positive. I'm going in this direction. Yeah? If I'm going in this direction, what's the sign of my velocity? Negative, isn't it? Because I'm going to more negative addresses. Yeah. Yeah. So it don't mean walking in the direction. That's a reasonable interpretation. It doesn't mean walking in the direction I'm looking at. It's just, how does my position change? Can I have a negative velocity when I'm going past positive addresses? Yeah, I can go in that direction. I've got a negative velocity, but I'm in positive addresses. Yeah. Yeah. Can I have a positive velocity when I'm going in negative addresses? Is that possible? Yeah. How do I know so? How can I tell? Well, I don't know how to phrase this actually. If I'm going in a positive velocity and I do this, am I speeding up or slowing down? Slowing down, aren't I? And what is my acceleration? Positive or negative? Negative. If I'm doing this, am I speeding up or slowing down? Slowing down. Stopping. And what is my acceleration? Positive or negative? So, can I link the sign of my acceleration to whether I'm speeding up and slowing down? Is it that positive acceleration means you're speeding up and negative means you're slowing down? Is it simple like that? Positive velocity meant I was going in that direction. Negative velocity means I'm going in that direction. Positive address means I'm over there. Negative address means I'm over there. Positive acceleration, no, you can't. It's not so easy. And I need to show you that because it turns out that it's not like that. So I'm going to show you a kind of a trick. Well, not a trick, it's just a simple way. Let's say that we have a velocity versus time table. And let's say that my acceleration is equal to plus 2 meters per second squared. Now, when I was at school, back in the last century, we'd say plus 2 meters per second every second. That's what they said. Meters per second. And that was like really good because I knew it was a velocity change every second. It really emphasized this is a velocity change every second. So I knew what to do. But then they said, but mathematically that equals meters per second squared. So they did that, which is mathematically correct. But it's like, now you've lost that hint about what it means. It's kind of gone. So, okay, every second I add on 2 meters per second to the velocity. So let's say I start off going in a negative direction. Let's say I start off going in a positive direction. So I'm going to have my time t equals 0. I'm going to have plus 10 meters per second squared. So what would I have at 11 meters, at time 1 second? What would be my velocity? Plus 12. And 2 plus 14. And 3 plus 16. And can you see I'm going faster and faster and faster and faster and faster, yeah? Okay, so positive velocity, a positive acceleration seems to have given me a speeding up, yeah? Oh, maybe it's right, but let's do this now. Let's do another one of these tables. But now let's say that I'm not going in a positive direction. I'm going in a negative direction. So let's say that my speed is my velocity is minus 10 meters per second at 0. And at 1, I'm going at, what would I do now? Minus 8. And then 2, minus 6. And then 3, minus 4. Am I speeding up or slowing down? I'm slowing down. My velocity, my speed is getting less and less and less. So I'm slowing down. So now positive acceleration gave me a slowing down. So positive acceleration sometimes gives you a speeding up, and a positive acceleration sometimes gives you a slowing down. And so the way we make head or tail of it is this. If I take my object and I have a positive velocity and a positive acceleration, I will speed up while going in the positive direction. Faster and faster and faster and faster and faster. If I have a negative velocity and a negative acceleration, I will speed up while going in a negative direction. It's when your velocity and the acceleration have the same direction, you speed up. So positive with positive, negative with negative, you speed up. In one case, you're speeding up going in a positive direction, and in the other case, you're speeding up going in a negative direction. But when those two are pointing in the same direction, you speed up. When I have positive velocity and a negative acceleration, I slow down. I'm still going positive direction, but I slow down. So when I have a positive vel and a negative acceleration, I slow down. I'm still going in a positive direction because it's the velocity gives me my direction, but I'm slowing down. And if I have a positive acceleration and a negative velocity, I slow down. I'm going in a negative direction in this case because it is the velocity that always gives you the direction. So you want to know your direction, you look at the velocity. You want to know if you're speeding up or slowing down, you have to look at both the acceleration and the velocity. If they're in the same sense, you're speeding up. If they're in the opposite sense, you're slowing down. Okay. And I can show you this, actually. This is kind of interesting. If I look back at this guy here, then at 4 seconds, I'm at -2, and at 5 seconds, I'm at 0. So this is slowing, going in a neg direction. And then what happens is, well, in 6 seconds I have +2, and 7 seconds I have +4, and 8 seconds I have +6. So now I am speeding up in a positive direction. And you know that when you take an object and you throw it up. When this is traveling upwards, the acceleration due to gravity is downwards. So its velocity is positive, but its acceleration is negative, so it slows down. It then stops at the top. It then starts traveling downwards with a negative acceleration, so it speeds up. And you see that, don't you? Yeah. So if this is like, this is unfamiliar to you, so you might not remember what to do. Just remember that visualization. If you can explain that in terms of velocity and acceleration, then you can explain whatever I ask for you. It's a good way of concreting, making it real, so that it's not just abstract. You're kind of like, oh yeah, I remember that example. So this is the take home. So when you're speeding up, when your acceleration is positive and your velocity is positive, you're speeding up while going in a positive direction. And in this case, you're speeding up while going in a negative direction. And in this case, I'm slowing down while going in a positive direction. In this case, I'm slowing down while going in a negative direction. And so I say, okay, at t equals 5 seconds, an object has a velocity of +2 meters per second and an acceleration of -8 meters per second squared. Characterize its direction of motion. It's going in pos direction and rate of progress while slowing down. Slowing down. It's going in a positive direction because my v is positive, and it's slowing down because my v and my acceleration are in opposite directions to each other. So there's not a simple rule for acceleration. There is for velocity and there is for address, but there's not a simple rule for acceleration. You've got to look at both of those. Okay. Can you do that one for me, please? So on this one, we basically imagine our object and we ask ourselves, what's the v doing, what's the a doing? The v is -12 meters per second, and the a is -4 meters per second squared, so I'm going in a negative direction. So going in a negative direction, that works for me, but that one doesn't. And that one doesn't. So it's between those two, and I am speeding up. So it's B on that one. What did we have? Mainly B? Can't find it. Mainly B? Yeah, mainly B. So, nice little question. Not obvious. Until you do a course like this, it's not obvious what the answer would be. Most people will get that wrong intuitively. It's really confusing. Let's talk about graphs. So graphs, don't write off graphs as being unimportant. My wife works in a much more technical field than I ever worked in, actually, doing harder science than I ever did, and she uses graphs all the time. Graphs are both clinically and also in terms of record keeping and also in terms of interpretation, graphs are really valuable. In terms of making developments, graphs are really valuable as well. Some things are very obvious from a graph that are not obvious from an equation, and vice versa. And a graph is a graphical representation of an equation. An equation is an abstract equation of a graph. They're the same thing. There's just two ways of writing down the same thing. These three graphs, one is a position or a coordinate versus time, one is a velocity versus time, and one is a acceleration versus time. They're not the same journey. If I have that acceleration in time, I cannot get that velocity in time. And if I have that velocity in time, I cannot get that displacement in time. They don't go together. They're just three linear representations. Because I want to raise a question of you what does the slope of these graphs mean, and what does the area under these graphs curves mean? Because they might mean something physically very valuable. And you can get the clue from the units. If I look at this first one, I can tell you that the slope is going to be a change, the rise. The rise is going to be measured in meters, and the run is going to be measured in seconds. So rise over run gives you meters per second. If it walks like a duck, and it quacks like a duck, and it talks like a duck, it's a duck. It's measured in meters per second, it's velocity. Okay? It's not acceleration, it's velocity, because velocity is measured in meters per second. If I look at the area under the curve, well, although it's not although it's a trapezoid, the fact of the matter is it's going to be some kind of meters multiplied by some kind of seconds. Meter seconds is a unit. It exists. It doesn't really lend itself to interpretation. So we say it's not got a clear physical meaning. It exists. It's something, but it's not useful to us. It doesn't mean something we can intuit. It's kind of like, I don't know what that means, really. It does exist, though. It's not like it's imaginary. It does exist. It just, I don't know how to interpret that. If I take a velocity versus time graph, then my slope is going to be meters per second divided by seconds. Oh, yeah, that's my old friend. Meters per second squared. That's acceleration. So you look at the slope of a velocity time graph, you get acceleration. Area under the curve would be meters per second times seconds. Oh, that's meters. That's displacement. That's really useful. I can look at that graph. I can get any slope, tells me the acceleration. Any area under the graph gives me the displacement. It's like a really useful graph. And then this third one is acceleration versus time. And the slope, again, I keep losing my pen, I'm sorry. The slope is meters per second squared divided by seconds, which is meters per second cubed. And actually, this is the more useful form. It's the change of my acceleration in time. Now, I put down there no clear meaning because I was thinking as a physicist. But engineers deal with this all the time. Anybody know what this is? Pardon? What do you say? Pardon? Hey, watch it. Be nice. Come on. Yeah, it means jerk. Okay? And jerk is like, what? You jerk something. What are you doing when you jerk something? You're kind of applying a sudden, rapid force. Boom. And that force is changing quickly, which means that acceleration is changing quickly in time. You hit it with a hammer. Big force goes away. You don't lean on the hammer. You bang it with the hammer. There's a whole bunch of reasons why you're doing that. There's a whole bunch of reasons why we tap some things and we push some things. Very different things. So this is jerk, and it's very useful. And then the area under the graph would be, again, I lost my pen. The area under the graph is meters per second squared times seconds, which is meters per second. Change in velocity. So it's like, boom. Very nice indeed. So then the next thing that I do is I ask you to interpret these things. So in truth, this is in seconds, and I could not easily make something that would change like this unless it was incredibly light. But imagine this was hours. I was driving along and all this kind of stuff. Then I could get something with nice sharp corners like that. Very hard to do in a machine that's got any mass to it. But on that time scale, but if I make the machine, if I increase the time scale, I can approximate this with my car. On a track, I could approximate it. So this is position. So first of all, people get the graphs confused because they don't pay attention to the axes. I'm not saying, you guys are no good. I was exactly the same, and I've learned the hard way by messing things up to always double check your axes, because if you think it's a velocity time graph and it's a position time graph, all the thinking about it is wrong. And so we say this is position time. So the slope means velocity. So that's a constant positive velocity. I can even tell you how much it is, because it's going to be plus 20 over 1, plus 20 meters per second. What does that bit represent? What am I doing there? I'm stationary, aren't I? My position's not changing. Another positive velocity, this time is 10 meters per second. And then I change direction. I'm no longer going in a positive direction, and now I'm going in a negative direction. So I change direction. I know I'm going in a negative direction because that's a negative velocity. Stationary again. Positive velocity. When do I return to my starting point? What time? 4 seconds, because I'm back at 0. What does the area under this curve mean? Meters seconds. Who knows? Okay. Look at this one. Positive velocity? No, positive acceleration, isn't it? Constant positive acceleration. Velocity versus time, constant positive acceleration. Then I change my positive acceleration. What does this mean? It's not static, is it? It's actually traveling at 15 meters per second. It looks like that, but it's a different graph. So this is actually a constant high speed, no acceleration. This was 0 velocity. This is 0 acceleration because they're different graphs. This is a negative acceleration. At this point here, so when do I turn around on this graph? Here, I turned around. I stopped going in a positive direction there, and I started going in a negative direction there. Where do I stop going in a positive direction on this graph and start going in a negative direction? Actually, it's not here. This is all about acceleration, isn't it? It's there. My velocity goes from being positive to negative. Here, my position went from positive to negative. Here is my velocity that's going from positive to negative. I turn around when I stop going positive and start going negative, or stop going negative and start going positive. This is 4.6 seconds. And you've got to get the 4.6. This is not 3 and 3. This is 5 steps. I'm 3 into my 5 steps, so I'm 3 into my 5 steps along, which is 0.6. And then, when would I return to the starting point? I'd return to the starting point when that displacement is the same as that displacement, if I ever get that. Can you see? 2 very similar looking graphs, completely different interpretation. And I can do the same thing over here. So the things I can do is I can say, what is the object's position and direction of motion at a specific time? Or what is an object's average velocity, distance traveled? What is a stopping time? So look at those. And I will see you guys next time. Don't forget, know your geometrical shapes. It's 3 easy points. Just learn them and just get the 3 easy points.